So another theorem about these sorts of differential equations. Now you'll notice we have some of the same conditions here that we had when we were talking about the existence and uniqueness theorem. We require that the coefficient functions be continuous. We require that the lead coefficient be non-zero. And we also require now here a little bit more, so the right-hand side is 0. So we're looking specifically at a homogeneous differential equation satisfying the conditions of the existence and uniqueness theorem. And of course this does satisfy the continuity requirement because of course the 0 function is continuous. Okay. So what this theorem says is that if those conditions are satisfied, in other words, for any homogeneous differential equation satisfying the conditions of the existence and uniqueness theorem, every solution is a Cn function, namely it's n times differentiable and the nth derivative is continuous. Furthermore, the collection forms a vector subspace of Cn, and even more so, it is an n-dimensional vector subspace, and n specifically is the order of the differential equation. Okay. So this is a neat theorem. We're going to make an enormous amount of use out of this theorem in this chapter. We're going to start by proving most of this theorem. We won't prove the whole thing right now, but we will prove most of it. I'll start with Cn. How do we know that these solutions to this differential equation are Cn? And the good news here, well, it's just not that hard to solve for this nth derivative of y. You can take all the rest of the left side of the equation, move it over to the right, like so, and then you can divide by that coefficient Qn. By the way, this is why we need Qn to not equal to 0. You can't divide by it if it's equal to 0. So that's nice. And lo and behold, we have solved for this nth derivative of y. And notice that what that nth derivative of y is equal to, everything here, all these coefficients are known to be continuous. Denominator as well. Furthermore, I know that all of these values and derivatives of y are continuous. Why do I know that they're continuous? Well, because we have a solution to this differential equation, which means that there is an nth derivative. That means that even the n-1th derivative has to be differentiable in order for that nth derivative even to exist. So if this is differentiable, but then it's certainly continuous. So what we have then is that yn is a combination of known continuous functions, and therefore it too is continuous. And that means, of course, if the nth derivative is continuous, that means that the function is Cn. Okay, so we have proved that. Okay. By the way, it looks like I forgot a minus sign here. Sorry about that. Okay, next, how do we know that these form a vector subspace? How do I know that that this complete set of solutions is a subspace? Well, we have a method for how to decide if something is a subspace, and that is you just check that it's closed under addition, you check that it's closed under scalar multiplication. So how do I know? Suppose that y1 and y2 are solutions. How do I know that y1 plus y2 is a solution? Well, I need to compute L of y1 plus y2. By the way, I need to make sure that it's equal to 0. That's what it would mean for y1 plus y2 to be a solution. Okay, so how do I know that that is actually true? Well, by linearity, I know that. And given that y1 and y2 are solutions, that tells me y1 being a solution gives me that, and y2 being a solution gives me that. And of course, 0 plus 0 is 0. And so as required, y1 plus y2 is a solution. So therefore, this set is closed under addition. Okay. And then very similarly, for being closed under scalar multiplication, we assume that y1 is a solution, and using linearity and that fact, we conclude that any scalar multiple of y1 must be a solution. Okay. All right. Now, there is, before I go on, this is a good callback moment. You look at this argument here, the algebra that we went into to show that this collection of solutions is closed under addition and closed under scalar multiplication. I strongly encourage you to do this. Go back and compare what we've just argued to a previous argument that we made about homogeneous solutions to matrix equations. We argued a very similar argument at that time, and it's worth making the observation that there is a strong similarity there, because this is an example of many similarities that we're going to notice here between homogeneous differential equations and matrix equations. Specifically, homogeneous linear differential equations and matrix equations. Okay. All right, now there is one last thing to confirm. We've confirmed that these are CN. We've confirmed that they form a subspace. It remains to consider the question of whether this subspace is n-dimensional. We do technically have tools that would allow us to prove this at this moment, but there's a lot of details. And very soon in the course, not far at all in the future, we will have some more powerful tools that will allow us to draw this conclusion more easily. So I'm going to delay this proof until we have this more powerful linear algebra tool called a linear transformation. Okay. All right, so we've established this theorem to the extent we're going to at the moment, and this proof is coming. And there's a big consequence of this theorem that we're going to take advantage of on the next page, and that is, roughly speaking, what this has done is it has taken the question of solving a differential equation, which appears at a glance to be an analysis problem. You know, calculus, that kind of thing. I mean, you see there's derivatives. You can suspect that there might be some integrals involved somewhere, and it just feels like basically a calculus problem. But what we realize now, what this theorem tells us, is that maybe it is, but it is also very much a linear algebra problem. This is not just a calculus problem. This is a linear algebra problem. We're trying to understand a linear algebra object. We're not just trying to find a bunch of solutions that have nothing to do with each other. We're trying to understand an n-dimensional subspace of a known vector space. So, an important realization, these kinds of differential equations, they're not analysis problems alone. They are linear algebra problems. Okay, and that's going to be enormously important as we go through the rest of the differential equations in this course. A little bit of lingo. Since we are talking about a vector space, we can talk about a basis for that vector space. Specifically, the vector space of solutions to the homogeneous linear differential equation. And this basis has a name. It's classically called a fundamental set of solutions. One could argue that this terminology is not needed. We could just call it a basis for the set of solutions, and that's fine, but this terminology is very much in the culture, and students should be aware of it. And in keeping with what everyone else does, we will also be using this term, fundamental set of solutions, throughout this course. But importantly, keep in mind what it is. It's just a basis. It's a basis for the vector space that we now realize is actually the object of our interest. Okay, so here's an example of how we can use this. Here's a differential equation. Easy differential equation to write down. Not immediately clear how you'd go about solving this. At a glance, what calculus methods would we use to solve this differential equation? Yeah. Seemingly a pretty hard problem. Okay, that in mind, we do note that it's homogeneous. We see from the form of the left-hand side that it is linear. And you notice that it is second order. You furthermore notice that these coefficient functions, being as they are 1, and there's a 0 y prime in there, and then this 1 y, all those coefficient functions are continuous. The lead coefficient function is never 0, because it's always 1. And, of course, the right-hand side, being the 0 function, is also continuous. So all of our conditions are satisfied, and we know from the previous theorem, then, that, again, we're not just looking for some solutions. We are looking for a vector space. subspace of C2. Okay, so we're not going to look at this question from a calculus point of view. We're going to look at this question from a linear algebra point of view. So we know that this vector space that we're looking for is two-dimensional. So if I can find by hook or by crook two solutions, maybe we get lucky. We find two solutions that aren't multiples of each other. In other words, if I can find an independent pair of solutions, then we're in good shape. And in fact, that happens here to us. Casual observation. Sine x works. Right? We all remember how to take derivative of sine, and everybody's noticed that when you take the derivative of sine, you get cosine. Take the derivative of cosine, you get negative sine. And so weirdly, the sine x is a function whose second derivative is the negative of itself. And therefore it satisfies this differential equation. Fine. And of course cosine, same thing. That also works. Right? So as required, we have found two solutions. They're not multiples of each other, therefore they're an independent pair of solutions in a two-dimensional vector space. And using our linear algebra theorems, we know that we have a basis. This pair here is a basis for our solution set. Being as they are a basis, that means that every solution is of this form. Every solution is a linear combination of those solutions. And we're done. Right? So you can write this in a couple different ways. You can say that this is the general solution. Or you might just prefer to take a linear algebra point of view and say that this is the fundamental set of solutions. Either way, it says roughly the same thing. Okay. So it's important to realize that linear algebra is what allowed us to do this. So when we did make the casual observation about a couple of specific individual functions, but ultimately the analysis contribution to this solution was to take a couple of derivatives, and we found with analysis two solutions. All infinite of the remainder of them we found with linear algebra. Right? It was the idea of the linearity of this differential equation that allows for these linear combinations to work. And it's our more sophisticated idea of the fact that the solutions are a two-dimensional vector space. So our idea of the fact that they're a vector space at all, and then our more sophisticated idea of what the dimension of a vector space is. These very significant linear algebra ideas are what allowed us to conclude not only that these are also solutions, but that because of the dimension, those are the only solutions. So there aren't other solutions out there that we might inadvertently find in the same way that we found sine and cosine. That's it. Just sine and cosine and its linear combinations.